So finite element method, 2D elements. So what are the examples of 2D element? Already we know that examples of one dimensional element is bar element and beam element. Already we have discussed also bar element and beam element. So coming to two dimensional elements, we have CST element. CST is considered as two dimensional element. Then we have LST. Then we have rectangular elements. Rectangular elements. These are considered as two dimensional element. Two dimensional means that will be having length as well as width, means we can find the area of that the given element. If we are able to find the area of a given element, we will consider that as a two dimensional element, right? So for CST, LST, CST is constant strain triangle, LST is linear strain triangle, and rectangular element. So triangle is also your two dimensional. We can find the area of a triangle. We can find the area of a rectangle. So that is considered as two dimensional elements. So these are the examples of two dimensional elements. Now, for analysis of these two dimensional elements like CST and LST, we usually use two conditions. We use two conditions. Two conditions to analyze this two dimensional element. First condition is plane stress condition. Plane stress condition, and second one is plane strain condition. Second one is plane strain. So while solving the problem, while analyzing this two dimensional element, we will have two conditions, plane stress or plane strain. So same problem we can approach with plane stress and plane strain. It depends what they are asking, whether they are asking from plane stress or plane strain condition, right? Then basically, if we will see, the two-dimensional problems is basically two-dimensional problems is basically divided into two parts. First, we say it as a scalar variable problem. A scalar variable problem, and second one is your vector variable problem. Vector variable problem, because in most of the book, if you will open, you will see a scalar problem, vector problem. So what is that scalar variable problem and vector variable problem? So let us see. A scalar variable problem means the problems related to scalar quantities. So problems related to a scalar quantity means what? The quantities which has no direction, no direction and only magnitude. Means if they are asking you to find some quantity which has only magnitude, no direction, means only magnitude. If they are asking you to find some quantity which has only magnitude, no direction, then that problem is called as a scalar variable problem. For example, if any problem of CST element, LST element or rectangular element, what type of problem? Heat related problem. Heat related problems. If they are asking CST, LST, analysis of CST element or LST element or related to heat problems, then that problem is considered as scalar variable problem. Generally, this type of problem will be for mechanical people. In mechanical engineering, there will be problems based on this heat related, right? Now, vector variable, you can understand now. Vector variable means will have magnitude as well as direction also. So if they are asking you to find some quantity which has magnitude as well as direction also, like forces, like force related problems. So here force related problem is basically in the civil engineering side. we are finding unknown forces, we are finding stresses, right? So these all are what? These all are your forces we are finding. Force is what? Vector variable, vector quantity, right? So that is why this type of problem will be called as vector variable problem. So whatever the problem we will come across, that all will be vector variable problem, because we are going to find unknown forces on all, right? If the same thing mechanical people will use, they will find these heat related problems, they will find the heat, so that will be called as a scalar variable problem. So in basically two-dimensional elements, there are two conditions: plane stress condition and plane strain condition. Based on the question details, we will identify whether we should go for the plane stress condition or plane strain condition. And then the problem is basically divided into two parts: a scalar variable and vector variable. Scalar variable means the quantities the quantities that they are asking will have only magnitude, no direction. But if the quantities they are asking having magnitude as well as direction, like they are asking some unknown forces, then it will come under the category of vector variable. So now let us see the difference between CST and LST elements, because I have given the example as for two-dimensional element, I have given the example of CST and LST. So what is the basically difference between CST and LST? Because when I said CST, constant strain triangle, LST, linear strain triangle, so both are triangular element itself. But what is the difference? So let us see. Let me take, this is CST, and here let me take as LST. Okay. So first point I am going to write here for CST element. So you can see CST element, both are two-dimensional elements. Already we have discussed these things, that CST as well as LST, both are two-dimensional element. These both are two-dimensional elements, right? But this is linear element. But CST is your linear element, and LST is again two-dimensional element but non-linear element. This is non-linear element. This is the first difference. CST, constant strain triangle, then it is called as linear element. Linear strain triangle, then it is called as non-linear element. Don't get confused, because I am saying this full form. Okay, I will write the full form here. Now CST stands for what? CST stands for constant strain triangle. LST stands for linear strain triangle. So you don't be confused. Sir, you are saying here LST means linear strain triangle, but you are writing non-linear element. Yes, this is linear strain. I am not saying that the elements are linear. The strain in this will be linear, and the strain in this element, triangular element, will be constant. It is not going to change. It will be constant throughout the element. But here it is going to vary. What is the variation? What type of variation is there? Linear variation. That's why it is called as linear strain triangle. Okay. So let us take, this is your point number one. Now coming to the third difference. If we'll see the third difference, what is the difference? The strain is constant throughout the rail. That's what, as per the name suggests, strain is going to be, strain is constant throughout the element. And here strain is varying linearly. Strain is varying linearly inside the element. So in this triangle, strain is going to be constant. In this triangle, the strain is going to be varying linearly. Now, fourth point I can say, fourth point is it has only, if you will see the CST element, it will have only 3 primary nodes at the corner. Only 3 primary nodes at corner. But in this case, there will be 3 primary nodes as well as 3 secondary nodes. 3 primary at corner and 3 secondary at mid side, middle of the sides. For example, if I will draw the triangle, let me draw the triangle, constant strength triangle element. Let us take, this is the element. So here we will have how many nodes? 3 nodes, node number 1, node number 2, node number 3, and at each node we will have, let us take, this is 1, 2 and 3, and each node we will have 3 displacements. Sorry, 2 displacement. At each node we will have 2 displacement. Let me take as in x direction, let me take displacement as u, so u1, and in y v1. Similarly, at node number 2 we will have u2 v2, at node number 3 u3 and v3. So this is your CST, constant strength triangle. See, only 3 primary nodes are there at the corners. But coming to LST, what I said, in LST we have 3 nodes at the corners as well as 3 in between. Means, let me draw that. So if I will see 3 primary nodes, same as CST, okay, 1, 2, 3. So let me mark it as 1, 2 and 3. And 3 more elements, 3 more nodes are there in between these side elements. So let me mark here. This is 4, at this point 5, and at this point 6. And similarly, we will have 2 displacement at each node. So this is u1, v1, u3, v3, u5, v5, and similarly you can write here u4, v4, v2, u2, v6, u6. So there are 6 nodes. 3 are the primary nodes and 3 are the secondary nodes. And each node we are going to have 2 displacements in x direction and in y direction. If I am taking this as x and y, in direction x direction and y direction, then 2 displacement. In x I have taken here u, and in y I have taken here v. So this is the difference between CST and LST. Now let us see the stiffness matrix for a CST element. What will be the stiffness matrix for a CST element? Let us see now. CST stiffness matrix for CST. Stiffness matrix for a CST element. So for CST element, the stiffness matrix is going to be K matrix is a stiffness matrix. It will be equal to integration, volumetric integration, right? Or you can represent as 3 integration here. I am writing V means volumetric. B matrix transpose of B matrix into D matrix into again B matrix into DV. So integration of B transpose into D matrix into B matrix into DB. Now we have to integrate this. So after integrating, what we get? See from here DB. So we can write DB as area into thickness, right? We can write this DB as area into thickness. So we can write directly now this stiffness matrix now, because this dV we can replace by area, means after integration this dV is going to be nothing, area into thickness. So this K matrix directly after integration we can write it as B transpose into D into B matrix into A into T matrix T. So this is your stiffness matrix. Just we need to see we need to find the transpose of B matrix into D matrix into B matrix into A into T. These all terms we will discuss. What are this D matrix? What is this B matrix, right? What will be the area? How will you calculate the area of the given triangle? Because they will not give the base into height, means half into base into height, means they are not going to give you base and height. So how will you, they will give the coordinates. So how will you calculate this area? We will discuss these things. Thickness, they will directly give the thickness, where T is your area. This A is area of element. Rather I can say CST element, because I am talking about CST only. T is thickness. Okay. B is called as strain displacement matrix. This B matrix is strain displacement matrix, or the other name is gradient matrix. Gradient matrix. Okay. Now this D matrix. Now coming to this D matrix. Now this D matrix, it depends on condition. It depends on condition. Now what are that condition? Plane stress, and second one is plane strain. So this D matrix depends upon plane stress and plane strain. So this will be the formula for finding a stiffness matrix. But if they are asking the stiffness matrix for a CST element having plane stress problem, then this D matrix is going to be different. If it will be for plane strain condition, then this D matrix is going to be different. So what will be that D matrix? Just already we have derived in plane stress and plane strain condition that D matrix compatible matrix, right? So directly I will write here first for plane stress. For plane stress, that D matrix is going to be, for plane stress problem, that D matrix is going to be E upon 1 minus nu square. Already we have derived these things in plane stress condition. D matrix 1 nu 0 nu 1 0 0 0 1 minus nu by 2. So if they have mentioned that the problem is plane stress problem, then the D matrix is going to be this. But if they are mentioning that this is plane stress problem, plane strain problem, if they are mentioning that this is plane strain problem, that then this D matrix is going to be E upon 1 plus nu into 1 minus 2 nu 1 minus nu 0, sorry, 1 minus nu, then nu 0, then again nu 1 minus nu 0, 0, 0, and 1 minus 2 nu by 2. This will be our D matrix. Everything will be given. E value will be given. New value will be given. If we will have E Young's modulus. E is your Young's modulus. E will be your Young's modulus, and nu is your Poisson's ratio. So every value will be given. If every value will be given, then only we need to put that value and we are going to get this D matrix. Once we will get the D matrix, it will be easy for us to calculate K, stiffness, right? Now area, how to calculate area? What will be this B matrix? So area. Area of the triangle. How you are going to calculate this area of the triangle? That will be half. In coordinate geometry, you might have studied this half, and then we need to find the determinant of 1 x1 y1 1 x2 y2 1 x3 y3. By using this, we can find the area of the element. This x1 y1 is the coordinates. So let us take this is the element. So if it is node number 1, the coordinates are going to be x1 y1. Node number 2, x2 y2. Node number 3, x3 y3. So this is the given element. Now you need to find the area. Just find the determinant 1 x1 y1, 1 x2 y2, 1 x3 y3, and half of this you are going to get area of the given element. Now coming to B matrix. This is very, very important. This matrix already you can find this matrix while deriving the stiffness, shape function of the CST elements. We have discussed this B matrix, that is 1 upon 2a into beta 1 0 beta 2 then 0 beta 3 again 0. Next 0 gamma 1 0 gamma 2 0 gamma 3. Next gamma 1 beta 1, then gamma 2 beta 2, then gamma 3 beta 3. So this is your B matrix. So now we know everything. Now in a stiffness matrix, if you want to find the stiffness matrix, this B transpose, you can find the B transpose because we know this B matrix. We know D matrix, it depends upon condition, whether it is plane stress or plane strain. On the basis of that condition, the D matrix is going to be different. How to calculate area? We know thickness they will give directly. B transpose, once you know the B matrix, you will be easily finding this B transpose. B transpose, how will you find? Simple. If you have this B matrix, just you convert this row into column. Just write this matrix like this: beta 1 0 beta 2 0 beta 3 0, then second one 0 gamma 1 0 gamma 2 0 gamma 3. Third one gamma 1 beta 1 gamma 2 beta 2 gamma 3 beta 3. This is your B transpose. This matrix is your, this is your B transpose matrix, right? So already we have calculated each and everything. So all now what they can ask. And this beta 1, beta 2, beta 3, already we have discussed what will be the value of beta 1, what will be the value of beta 2, what will be the value of beta 3, gamma 1, gamma 2, gamma 3. While deriving the shape function of the CST element, we have already discussed this thing, what is beta, what is gamma, what is, still I will write here what will be beta 1. So beta 1 will be directly, we can write it as y2 minus y3. That will be y2 minus, what is this y2 y3? The coordinates. Y2 minus y3 value will give you beta 1. Beta 2, beta 2 we will find as y3 minus y1. Beta 3 we can find it as y1 minus y2. So 2 3 3 1 1 2, it is in sequence itself. So by the, or if you will remember the first one, you can remember the second and third also. Beta 1 2 3, then next again 3 1, then next 1 2, then gamma 1. Gamma 1 is going to be x3 minus x2. Gamma 2 will be now x1 minus x3, and gamma 3 will be x2 minus x1. Just opposite. If you remember this, just reverse it. This is y3, y2. So 3 is at last, so 3 will become first, 2 will become last. Only in place of y, you have to keep x. So x3 minus x2. Here, we can write without seeing this also, I can say gamma 2 is going to be x1 minus x3, x1 minus x3. Here, y1 minus y2, so reverse it, y2 minus y1. So in place of y, you can put x. So x2 minus x1, x2 minus x1. So remembering this is easy. So these are the value. Now, apart from this, you should know some basic formulas, because in this problem they can ask some basic things also to calculate. What are the basic formulas? That I will give you one by one. Note the first one. The first one is, if they are going to ask you a strain, calculate a strain, then directly the B matrix, already I have told what is B matrix, into delta matrix. If you know the displacements and if you know the B matrix, you are going to get this strain matrix. So if strain will be equal to B into delta, so directly they can ask calculate strain. Next, second one, this is very important, very important. Normal stress, it is all about normal stress. So sigma will be equal to, let me say, n. Half these formulas all I am taking from strength of materials, principal stress, principal strain, right? Half into sigma xx plus sigma yy plus minus root under sigma xx minus sigma yy whole square plus 4 tau xy square. So this is the formula for finding normal stress. If they are asking you to find the normal stress, you are going to apply this, because whatever the stress you will get, that you will get whether in principal, that is in x direction, in y direction, right? So sigma xx and sigma yy you can calculate. So by using this formula, you can find the normal stress. If you will write here, see, if I am going to use this plus sign, then we are going to get maximum. If you are going to use this minus sign, you will get minimum. So maximum normal stress will be half sigma xx plus sigma yy plus minimum will be here, in place of plus we will apply minus. So they can ask this also, calculate maximum normal stress, calculate minimum normal stress. Then they can ask one more thing, that is they can ask one more thing, maximum shear stress. They can ask maximum shear stress also. So maximum shear stress, how will you calculate? Tau max. They can ask this also. Calculate maximum shear stress. That will be half sigma 1 minus sigma 2. Sigma 1 is maximum normal stress, sigma 2 is minimum normal stress. Directly you can calculate from here, or else you can calculate, if you have not calculated normal stresses, then half sigma xx minus sigma yy whole square plus 4 tau square xy. Yeah, one more thing. This all formula you have studied in strength of material. Nothing new. I am not going to discuss anything new here. All everything you know. They can ask principal angle also. Principal angle. Angle. Right? That is theta p. So theta p will be half tan inverse. This is half 2. Tan inverse 2 tau xy upon sigma xx minus sigma yy. So these are the formulas that are important while we will solve the problems based on CST elements. This will be the additional formula. I can say these are the additional formulas, because apart from the stiffness matrix, they can ask these things. Mostly they will ask you to calculate the stiffness matrix, but apart from that, if they have given some data for the stiffness matrix so that it will become easy for you to calculate, then additionally they can ask you to calculate a strain. Additionally, they can ask you to calculate maximum normal stress or minimum normal stress. Then they can ask you to calculate maximum shear stress, and then they can ask you to calculate the principal angle, that is theta p. So this is all about the basic of this two-dimensional element, especially CST and LST elements. So in the next class, we will discuss isoparametric formulation. Okay. Right. So these formula you should remember, you should just see this formula. This is very basic formula, nothing else.